Hey everybody, welcome to section 4.1. This is a pretty big section, so hopefully you haven't procrastinated until right before class, but chapter 4 is maybe my favorite chapter in the book. It's one of my favorite things in linear algebra. It's super applicable to a lot of other things like differential equations, dynamical systems, and probability, and a lot of real life applications of that stuff. Now, there's a lot of these warm ups. These are to review stuff from 1.6 and 1.7, stuff about bases and coordinates and dimensions. So you'll need to review that if you haven't already mastered it. And for the other questions here, you better pause the video because the answers will appear in 3, 2, 1. And here are those solutions. Exercise 2 is false because you only have two vectors. That means the span of these two vectors is not all of R3. It requires three vectors to make a basis of R3 so that you can span R3. Exercise 3, yeah, this list of two vectors here is linearly independent, which means it meets one part of the definition of a basis. And also, we want to check that it spans the span of itself, which it definitely does. So that makes it a basis of the span of itself. So it's a basis of this two-dimensional subspace of R3, even though it's not a basis of R3. For exercise 4 and exercise 5, these are both false because the list is linearly dependent, and that means it can't be a basis of anything, because every basis needs to be linearly independent. Exercise 6, here are some of the answers, except I forgot part D. Anyways, part A, what we're trying to find is the B coordinates of 6, 0. And those are, what do you need to scale these basis vectors by so that that linear combination gives you the point 6, 0. And that is 1b1 and 1b2. So the B coordinates of 6, 0 is the vector 1, 1. With part B, it's asking what is the y, and if it gives you the B coordinates of y, that's telling you how to scale b1 and b2 so that the linear combination you get is y. And that result comes out to be y is 12, 12. Likewise with part C, we are trying to find the B coordinates right now. So the B coordinates, again, are like where you go on this different slanted grid. And you have to go 1 in the B1 direction and -1 in the B2 direction. That takes you to the point -2, 4. So the B coordinates are 1, -1. And likewise D, here again we're given the coordinates. That means that's how much we're scaling B1 and B2. And when you do that linear combination, the result should be 12, -12, which doesn't show up on the grid, but you can imagine if you went like -2 in the B1 direction, so opposite of B1 and twice as long, and then 4 doesn't fit here, but 4 times B2, you're going to like the point on the slanted blue grid here with coordinates -2, 4, which takes you to the point that is actually 12, -12. Okay, so that's exercise 6. Exercise 7. For A, there's a lot of ways you could say that P is invertible. You could use the invertible matrix theorem, which says that if you know that you have a linearly independent list of vectors as the columns, and we can tell these are linearly independent by looking at the picture, or if you can see that they span all of R2, that's enough. You could also use the determinant thing where the determinant comes out to be non-zero. A lot of ways to do it. For part B, we found the B coordinates of 6, 0. They were 1 and 1. So this is just checking that, like, when you do this linear combination of these columns using 1 and 1 as weights, you actually get 6, 0. So same idea as the way we did it in chapter 1. We're just thinking of it in terms of matrix by vector multiplication here. For part C, P inverse should come out to be this matrix here. And for part D, what we're checking is that the B coordinates of y, which we said here were 6, 0, right? Do we get that by doing this P inverse that we just found times the y that we found? The y that we found in the last exercise was the vector 12, 12. And yeah, when you do this, this works. Now, this equation here is basically saying the same thing as P times the B coordinates of y should equal y. We're just, moving the P to the other side because we know it's invertible. You can multiply P inverse on both sides. And this equation here is basically just the definition of B coordinates, right? The B coordinates are the scalars that you multiply by the columns of P, which are basis vectors, to get your y vector as a result. And for exercise 8, hopefully you reviewed the invertible matrix theorem and convinced yourself that a list of vectors is a basis. If you have C vectors, the right number of vectors, that's a basis of RC, if and only if the matrix that has those columns is invertible. And yeah, hopefully you're getting help if you don't see why that is, if you can't use the invertible matrix theorem to explain that. So anyways, I'll see you in the next video where we really dive into some applications of difference equations, which is going to relate to diagonalizability. And we'll see what all that means soon.